All right, hello everyone. This is the reading of the Energy in the Atmosphere reading selection, the homework assignment reading selection. This is Miss Brain from the Aquarius team, but hopefully everyone who's watching this is benefiting from it. Before we get started, I just want to show you a few quick things about looking at textbook readings that might really help you. So the first thing that I wanted to show you is that looking at these guides for reading, right over here on the left-hand side, they can be very helpful in helping you know what information is going to be the most important as you're reading through this text. So this guide for reading, for instance, says, in what form does energy from the sun travel to Earth? So you know that if you're able to answer that question when you're finished, then you will have understood the main point that they wanted you to. And then the other one that they have here, it says, what happens to energy from the sun when it reaches Earth? So if you would be able to explain that, say, to like a little brother or sister or neighbor, whoever, parent, guardian, somebody, if you were able to explain sort of those two things, then you would have taken away the most important stuff that you needed to from this reading. And then this reading tip is super duper helpful. So it says, before you read, skim the selection for boldface words that are unfamiliar to you. As you read, find their meanings and write them down in your notebook. So I always say when you're taking notes, you want to look for the bold type, and that should be your main points, right? So maybe here for this first one, your main point in your note would be energy from the sun. And then you see that there are a few boldface words here. Electromagnetic waves, you'd want to define those. Radiation, you'd want to define that. And then clearly this whole sentence in bold is a big main idea that you need to write down too. So hopefully that is helpful for you. And of course, if you ever need any guidance on that, you can come see me, especially if I'm your teacher, or one of your other teachers as well. I'm sure they would be happy to help you out. So I'm going to start reading now, and every now and then I'll pause, explain something a little bit more, and maybe show you an image since I know some of these copies did not come out well, and then we'll be done. All right, here we go. Think of a sunny summer day. When you get up in the morning, the sun is low in the sky and the air is cool. As the sun rises, the temperature increases. By noon, it is quite hot. As you will see in this chapter, heat is a major factor in the weather. The movement of heat in the atmosphere causes temperatures to change, winds to blow, and rain to fall. Energy from the sun. Nearly all the energy in Earth's atmosphere comes from the sun. This energy travels to Earth as electromagnetic waves, a form of energy that can travel through space. Electromagnetic waves are classified according to wavelength, or distance between waves. The direct transfer of energy by electromagnetic waves is called radiation. Okay, so the main point here is all energy comes from the sun. All energy in Earth's atmosphere comes from the sun. And that sunlight energy comes in the form of electromagnetic waves. And the transfer of energy, so the transfer of energy from the sun to the Earth, that transfer of energy is called radiation. Most of the energy from the sun reaches Earth in the form of visible light and infrared radiation, and a small amount of ultraviolet radiation. Visible light is a mixture of all the colors that you see in a rainbow: red, orange, yellow, green, blue, and violet. Don't forget indigo. The different colors are the result of different wavelengths of visible light. Red and orange light have the longest wavelengths, while blue and violet light have the shortest wavelengths. Infrared radiation is a form of energy with wavelengths that are longer than red light. Infrared radiation is not visible, but can be felt as heat. Heat lamps used to keep food warm in restaurants, or the school cafeteria, give off both visible red light and invisible infrared radiation. The sun also gives off ultraviolet radiation, which has wavelengths that are shorter than violet light. Sunburns are caused by ultraviolet radiation. This radiation can also cause skin cancer and eye damage. So, basically what you're hearing here is that this radiation, this energy coming from the sun, is in the form of radiation, and there are the three kinds. There's the visible light, which we can see. There's infrared radiation, which is why when you're standing outside in the middle of a field on a sunny day, your skin starts to feel warm from the sun. Okay, you can't see that infrared radiation, and you might think it's the visible light that's actually heating up your skin, but it's not. It's the infrared radiation. That is a major heat source. And then the last one, you've probably heard of this before. This is why you wear sunblock. Ultraviolet radiation, okay, UV rays. These can be very damaging to our skin. It can cause skin cancer. And just like you might have learned learning about solar eclipses, you don't want to stare at the sun because it can cause eye damage as well. Let's take a very quick look over at a better image of the electromagnetic spectrum. This is not something that you need to know a ton about, okay? But it's helpful just to know a little bit about it as we go through the chapter, as you learn about other forms of energy. So here's the electromagnetic spectrum, okay? Over here you have waves that have long wavelengths, meaning that from the top of this hill to the top of the next hill is a lot longer, okay? Compared to down here, which has short wavelengths, which means those bumps in the wave, they're really close together, okay? So when you start at this end, when we're talking about this, if you look here, this is like an up close. So down here at the bottom is like an up close of what you are seeing right here, okay? Infrared has longer wavelengths than red light, okay, than the red from visible light. And then this here, the rainbow that you're seeing, that's all different types of visible light, right? You've heard that the, I don't know why that happened. You've heard that the rainbow is made up, that visible light is made up of the rainbow, and that's what you have here. And then on this end, you have ultraviolet light, where you have shorter wavelengths. So that's really all you need to know from this, knowing that things like radio and microwaves and X-rays and gamma rays, these are all parts of the electromagnetic spectrum. That's just good to know, but not essential information for you to keep in mind. Okay, let's go back to the reading. Energy in the atmosphere. Before the sun's rays can reach Earth's surface, they must pass through the atmosphere. The path of the sun's rays is shown in Exploring Energy in the Atmosphere on the following page, which also copied poorly, so I'll pull up a better picture of it in just a minute. Some of the energy from the sun is absorbed within the atmosphere. Water vapor and carbon dioxide absorb some infrared radiation. The ozone layer in the stratosphere absorbs most of the ultraviolet radiation. Clouds, dust, and other gases also absorb energy from the sun. So in this paragraph, you're hearing all about the different things that absorb energy from the sun. Water vapor and carbon dioxide are super important in that. They absorb a lot of energy from the sun. The ozone layer is important to us humans because it absorbs a lot of ultraviolet radiation coming from the sun. So that helps protect us from some of that dangerous radiation. And then also things like clouds, dust, and other gases in the atmosphere are absorbing some of that. Okay, some of the sun's rays are also reflected, meaning sent back. Clouds in the atmosphere act like mirrors, reflecting some solar energy back out into space. In addition, dust particles and molecules of gases in the atmosphere reflect light from the sun in all directions. Reflection of light in all directions is called scattering. When you look at the sky, the light you see has been scattered by gas molecules in the atmosphere. Gas molecules scatter shorter wavelengths of visible light, remember that was on the blue and violet end, more than long wavelengths, which is like red and orange. Scattered light is therefore bluer than ordinary sunlight, which is why the daytime sky looks blue. When the sun is rising or setting, light from the sun passes through a greater thickness of the atmosphere than when the sun is higher in the sky. More light from the blue end of the spectrum is removed by scattering before it reaches your eyes. The remaining light from the sun contains mostly red and orange light. The sun looks red, and clouds around it become very colorful. All right, let's look at a better picture of this. I mean, mildly better. So, here you have that image, but with text that you can actually read. So here's the sun's energy. It's visible light. Remember, we talked about it being infrared, a little bit of ultraviolet, and visible light. As those sun rays come in, a bunch of different things are happening to them. Some of it gets reflected back into space, only about 20%. Okay? 20% is also absorbed by the atmosphere, by gases, dust particles, clouds, things like that. So clouds can both absorb and reflect sunlight. Here you go. This is the big whopper. 50% is absorbed by the Earth's surface, so that heats up the land and the water. 6%, so very little, of the sunlight is reflected back into space by Earth's surface. So some of it actually reaches Earth's surface and then is sent back into space. And then about 4% of the energy that's absorbed here, absorbed into the land and water, about 4% is radiated back into the atmosphere by Earth's surfaces. So as the Earth heats up and loses, it then starts to give off some of its energy. And so some of that is radiated back into the atmosphere. All right, let's go back to the reading. Energy at Earth's surface. Some of the sun's energy reaches Earth's surface and is reflected back into the atmosphere. That's what we were just saying. Some of the energy, however, is absorbed by the land and water and changed into heat. When Earth's surface is heated, it radiates some of the energy back into the atmosphere as infrared radiation. So remember, infrared is the same kind of radiation that's coming from the sun. The land can absorb it and then send some back out. Most of this infrared radiation cannot travel all the way through the atmosphere back into space. Instead, much of it is absorbed by water vapor, carbon dioxide, methane, and other gases in the air. The energy from the absorbed radiation heats the gases in the air. These gases form a blanket around the Earth that holds heat in the atmosphere. The process by which gases hold heat in the air is called the greenhouse effect. So the greenhouse effect is basically heat energy that's being radiated back from the Earth into the atmosphere, which should be able to escape back into space, doesn't always happen, okay? Because some of the gases in the air are actually kind of trapping it in and forming almost like a blanket around the Earth that holds the heat in. So the way that a blanket works when you put it on you is the heat coming from your body actually gets trapped underneath the blanket and sort of stays closer to your skin and heats up the air under the blanket and heats you back up. Okay, so it's sending your own energy back at you. That's kind of like what the atmosphere is doing with the greenhouse effect. So I'll keep reading. Have you ever been inside a greenhouse during the winter? Even on a cold day, a greenhouse is warm. Greenhouses trap heat in two ways. First, infrared radiation given off in the interior, inside, cannot easily pass through glass and is trapped inside. Second, warm air inside the greenhouse cannot rise because the glass blocks the movement of air. What happens in Earth's atmosphere is similar to the first way that greenhouses trap heat. So they're saying the first way was infrared radiation given off inside can't really pass through the glass and gets trapped in. That's the same thing that happens with Earth's atmosphere if you imagine the atmosphere being like the glass of the greenhouse. The greenhouse effect is a natural process that keeps Earth's atmosphere at a temperature that is comfortable for most living things. Human activities over the last 200 years, however, have increased the amount of carbon dioxide in the atmosphere, which may be warming the atmosphere. You will learn more about that, blah, blah, blah. You won't, because you're only reading this section, which is good. But this is a really important point. So the greenhouse effect is a natural process. This was always happening. The greenhouse effect is not a bad thing. Okay? We need the greenhouse effect in order for us not to be freezing at night when we're on the other side pointed away from the sun and we don't have the sun's energy to heat us up. Okay? That greenhouse effect traps some heat in so that nighttime doesn't get too cold. Okay? However, it says here, in the last 200 years, human activities have increased those greenhouse gases like carbon dioxide, methane, things in the air that are trapping that heat. So too much heat is getting trapped in, and that's where climate change starts to happen. So we'll talk more about that later on. You can take a look at this diagram here too. You can see sunlight is coming into the earth. Okay, this is the earth. This all is the atmosphere here. Okay, sunlight is coming in, being absorbed by the land, and then given off as infrared radiation. But some of the gases in the air are trapping that heat in. So that's what this diagram is trying to tell you. If you look here at figure 2, sunlight travels through the atmosphere to Earth's surface. Earth's surface then gives off infrared radiation. Much of this energy is held by the atmosphere, warming it. All right, let's move on to the article on hurricanes. What are hurricanes? Hurricanes are large tropical storms with heavy winds. By definition, they contain winds in excess of 74 miles per hour, also known as 119 kilometers per hour. And they include large areas of rainfall. In addition, they have the potential to spawn dangerous tornadoes. The strong winds and excessive rainfall also produce abnormal rises in sea levels and flooding. Christopher Columbus was the first European in modern times to write about the hurricane. The Indians of Guatemala called the god of stormy weather Hunrakan. Similar names were probably present throughout the Caribbean. Captain Fernando de Oviedo gave storms their modern name when he wrote, "So when the devil wishes to terrify them, he promises them the huracan," which means tempest. Tempest is like an Old English word for storm. The same storms in other parts of the world are known as typhoons, bakulros, Bengal cyclones, and willy willies, which is my personal favorite. The ocean water temperature has to be above 79 degrees Fahrenheit in order for a hurricane to be generated. So they normally form in late summer and early fall when the conditions are right. So in class we talked about the hurricane season, and I said it's from August to about November. Well, August to November in the northern hemisphere, right? But you have to think about when summer and fall would be in the southern hemisphere because they can experience these types of storms as well. Meteorologists use the term tropical storm when a storm's winds are under 74 miles per hour, and hurricane when the wind speed rises. A hurricane has a peaceful center called the eye that is often distinctive in satellite images. The eye stretches from 10 to 30 miles wide and often contains calm winds, warm temperatures, and clear skies. Around this tropical bliss is a frenzy of winds gusting at speeds up to 186 miles per hour. If 1% of the energy in one hurricane could be captured, all the power, fuel, and heating requirements of the United States could be met for an entire year. It takes 500 trillion horsepower to whirl the great core of winds at such tremendous speeds. It is the equivalent of exploding an atomic bomb every 10 seconds. I want to pause here and talk about something we read at the beginning of this paragraph, which says the ocean water temperature has to be above 79 degrees. So, degrees Fahrenheit. So these storms normally form in late summer and early fall. Remember, when we were doing the soil and water lab, or when you get to it if you haven't yet, that soil heats up faster than water, right? It takes water a longer time to heat up. Water just takes a while to warm up. So it doesn't warm up from the summer heat until later into that season, okay? So that's really important. That is a big factor about why hurricanes happen late in the summer and then in the fall. Because we also will learn, or have learned from the Soil and Water Lab, that water takes a long time to lose its energy as well. So it holds on to that heat for a while. So even if you start to get cooler days in like September, October, the water might still be warm. All right, let's move on to the next section. How are hurricanes formed? Hurricanes begin as tropical storms over the warm, moist waters of the Atlantic and Pacific Oceans near the equator. Near the Philippines and the China Sea, hurricanes are called typhoons. As the moisture evaporates, it rises until enormous amounts of heated, moist air are twisted high in the atmosphere. The winds begin to circle counterclockwise north of the equator or clockwise south of the equator. The relatively peaceful center of the hurricane is called the eye. Around this center, winds move at speeds between 74 and 200 miles per hour. As long as the hurricane remains over waters of 79 degrees Fahrenheit or warmer, it continues to pull moisture from the surface and grow in size and force. When a hurricane crosses land or cooler waters, it loses its source of power, and its winds gradually slow until they are no longer of hurricane force, which means it is less than 74 miles per hour. Hurricanes over the Atlantic often begin near Africa, drift west on the trade winds, and veer north as they meet the prevailing winds coming eastward across North America. Hurricanes over the eastern Pacific begin in the warm waters off the Central American and Mexican coasts. Eastern and Central Pacific storms are called hurricanes. Storms to the west of the international dateline are called typhoons. So, in Asia, they're called typhoons. Because of the destructive force of hurricanes during the late summer and early autumn, scientists constantly monitor them with satellites and sometimes even fly airplane surveillance to keep track of tropical storms that might develop into hurricanes. That is the reading. If you have any questions, you should definitely reach out to your science teacher.